we are working on cross products, and my goal is to get them finished so that you'll be able to do all your homework. So imagine that you've got two vectors, A and B. The cross product would be a vector that is orthogonal to these two. In my picture here, wouldn't my pen that's sticking out of the paper probably be what A cross B would look like, right? Because we're talking three-dimensional world. And we've already yesterday showed you the mechanics of how to get the cross product. And it's a very visual thing, right? You know, the IJI, Cairo, and all the other stuff that comes later. So here's the new guy. The magnitude of the cross product, right? So those two lines mean the length of the vector, right? The magnitude of this cross product is the magnitude of A times the magnitude of B times the sine of theta. Does that look sort of a kind of similar to something that you saw earlier in the week? What's the magnitude of A times the magnitude of B times the cosine of theta?
Dot product.
Right. But the dot product doesn't need absolute values around it, because isn't the dot product a scalar? It's a number. But isn't this a cross product, and therefore this is a vector? And so these convert that into a number. Is that not interesting? The two different products, at least in this situation here, don't they almost meet? They almost become the same thing. So if I tell you the magnitude of two vectors and the angle between them, shouldn't you be able to find the magnitude of their cross product? So you're not finding their cross product. What you're doing is finding out the length of that cross product, right? So it's not quite the same as, you know, this, but that's fine, right? That's what that guy is. So imagine I gave you a question where I told you the magnitude of this was 2, and the magnitude of this vector was 4, and angle theta was, say, 45 degrees. And the question would simply just be, find the magnitude of its cross product. You would say 2 times 4 times the sine of 45 degrees. And that would become 8 times root 2 over 2. And that would be 4 root 2, because we always want exact values, right? We don't want 1.2345. And there are questions, I'm trying to find one right now, that do exactly that. You can never find them when you want them. Question 11 looks a bit like that. This is quite a long question, but I'm going to have to do it anyway, just so you can see it once. We're going to do a triple cross product. So I'm going to do a vector A, which is going to be 1, 0, 2. The vector B, which is going to be 1, minus 1, 3. And the vector C, which is going to be 2, 1, 4, right? And you are going to be asked to find some cross products of cross products. They're a triple cross product. Now, when you see it written this way, the brackets aren't just for cosmetic purposes. What they're telling you is find this guy first. Also, have you noticed that when you do cross products, who's first and who's second does mean something, right? Because if you switch places, don't you get the negative of the first answer, right? So we have to be pretty sure that we're doing it in the right order. So I'm going to do the cross product of B and C. So that's going to be I, J, and K. And the vector B is 1, negative 1, 3. And the vector C is 2, 1, 4. And that's going to be so many I's take away so many j's, plus so many k's. And there's my nice little piece of paper that I like. I'll use my pen, that'll do. If you cover up that guy, you get -4 take away 3, which is -7. If you cover up the j column, you get 4 take away 6, which is -2. If you cover up the k column, you get 1 take away -2, so you get 3. And so the answer is -7, +2, +3. And we now have kind of halfway, right? We got that guy. And now we're going to do A cross this guy. So I'll set up my I, my j, my k. And A is 1, 0, 2. And this guy is -7, 2, 3. So many i's, take away so many j's, plus so many k's. Cover that guy up. 0 take away 4 is -4. Cover up the middle one. 3 take away -14 is 3 add 14, so you get 17. And this last one, 2 take away nothing gets you 2. And so we have -4, -17, and 2. And we've just done our first triple cross product. Couldn't you do 4, 5, 6, or 7 cross products? I mean, you could do it almost unlimited number. Agreed? No. That guy is, as I mentioned, that's like 13. See if there's any more like that. Probably not, because there's so many things you can do with cross products. They're not all going to be here. No, that's the only one I can see. There might be another one, but that's the only one I can see. Now, suppose I've got two vectors, A and B again. And let's make that guy A and that guy B. And I find the magnitude of those two guys. And, you know, I'm just going to do it the normal cross product way, right? Not the magnitude of A, magnitude of B, sine theta thing, right? We're just going to do it that way. That number, right? And it's a length, so it's a positive thing, right? It's a length of a vector, so it's a positive thing, has a geometric property. Can you imagine I added 2 more parallel lines? Wouldn't 2 vectors in 3D space make a parallelogram? Can you imagine 2 vectors making a parallelogram? Here's something amazing. The magnitude of the cross product is the area of the parallelogram that's formed by the 2 vectors A and B. There is nothing intuitive about that to me. Would you agree? Why should a vector that's perpendicular to A and B, why should the length of that vector have anything to do with the area of the parallelogram? Would you agree? It doesn't make sense. But it's true, which is amazing. Now, if you take this parallelogram and you draw a line down here, would you agree that you break the parallelogram into 2 pieces of equal area? Then doesn't that mean that half the magnitude of the cross product is the area of the triangle formed by the 2 vectors? Well, if that's true, this is more obvious. Agreed? Now, if I write down 1/2 the cross product of A times B, and I rewrite the cross product as 1/2 the magnitude of A, the magnitude of B sine theta. Do you see a formula that is very close to being 1/2 AB sine theta? Do you recognize that formula? Isn't that from trig, the area of a triangle of side A, of lengths A and B, and the angle between them is theta? Have you ever wondered where the formula 1/2 AB sine theta comes from? Do you now know where it comes from? Amazing. There's something to do with cross products. We generate such weird, for want of a better word, weird geometric results. There's an area of parallelogram question, and there's a couple of them floating about. Version of this is 15. I'll do a version of that in a minute. 16. Sort of a 17. 18. Okay. There's a lot more than I thought. As I'm just scrolling through them here. Right. So there's what, 5 questions that are going to use this property to do with the magnitude of a cross product. So we are, there are different flavors of that question. So I'm going to try the hardest one. Suppose P is 1, 2, 4. Q is 1, 5, 1. And R is 0 to -1, right? So can you imagine P, Q, R, right? And we are going to use that information to find the area of the parallelogram and the area of the triangle. And the triangle would be the PQR one, right? You know, if you find one, don't you just half it and you've got the other? So it's not really a big deal to be asked both. Now, to do this question, don't we have to construct 2 vectors? You know, it be our A and our B, right? And so PQ is going to be 1 take away 1, 5 take away 2, and 7 take away 4. And the other vector, PR, is nothing take away 1, 2 take away 4, and -1 take away 5. Interesting. A lot of zeros. And if I want to find the area of the parallelogram, then don't I just find the magnitude of this guy's cross product? And if I want to know the area of the triangle, don't I find the magnitude of this cross product and then half it? So let's find the cross product. PQ cross PR. And we get an I, we get a J, we get a K, and we get 0, 3, 3, -1, 0, -5. And so many I's, take away so many J's, plus so many K's. Right, I'll cover this guy up. And what do you get? -15 take away 0, so it's -15. Cover this guy up, you get 0, take away -3, so that's 3. You cover this guy and you get 0, take away -3, and you get 3. So we are left with the cross product is -15, -3, and 3. So far, so good. So suppose the first question will be the area of the parallelogram. Well, that's the magnitude of this fella, right? So it's the magnitude of the cross product that we just found. And so that's going to be the square root of -15 squared plus -3 squared plus 3 squared. So that's 225 plus a 9 plus another 9, 18, 243. And I'm just going to assume that that can't be simplified. You might prove me wrong, but let's say you can't simplify it. Now, if you want to find the area of the triangle, isn't it just a half the area of that guy? So in three-dimensional space, if you tell me two vectors, like these two guys here, I can tell you the area of that triangle. I don't have enough hands. I could also tell you the area of the parallelogram it would make. And both of those are dependent on the magnitude of the cross product. Are we good? Let's look at what's called the triple product, sometimes the triple dot product. And it's this guy. So the triple dot product is a combination of a dot product and a cross product, right? It's got both happening. Now, we already did the A cross B cross C version. Do you see how this is a little bit different, right? It's a dot product of B cross C, right? And we can certainly calculate that. But before we calculate that, let me tell you some interesting properties about this thing, right? Is this going to be a vector when I'm finished or a scalar? Is it going to be a vector or just a single number? Which is it?
A scalar?
Yeah. Would you agree B cross C is just a vector? And then isn't a dot product, you know, a vector, dot product, a vector? Doesn't dot products always give you a number at the end, right? A scalar. So it is a scalar. Now, what on earth does that number represent geometrically? Remember, the magnitude of the cross product ended up being areas of parallelograms and triangles, right? That was quite interesting. It would be quite interesting if this had a meaning as well, wouldn't it? But you probably wouldn't guess what it gives you. And it's really quite cool. I want you to imagine that I have B and C being those two. And let's say A is a vector going something like that. So can you imagine that's my three vectors, A, B, C, right? If you take this guy and this guy, can you see you make a parallelogram on the fly? If you then take this guy and you build four of them parallel to him and you join them all together, you get a shape that looks like a three-dimensional box, don't you? And will you try not to see right angles? I'm just bad at drawing. Can you think of it as a box that the dog sat on and it got all squished? It's more like a three-dimensional parallelogram, right? It's got a really cool name, and I love saying this name. That shape is called a parallelepiped. Oh, come on, doesn't that name just roll off your tongue? Shouldn't a dwarf have been called that? Here's parallelepiped. I mean, it sounds like it should be in Lords of the Rings somewhere, right? If you're not a Lords of the Ring aficionado, okay. This scalar product is actually the volume of, I'll just call it P because I don't have enough room to write parallelepiped. Oh, come on, that is totally not intuitive. There's no reason in the world why that weird combination of dots and crosses, right, should ever give you anything to do with the volume of that shape. Would you agree? It's amazing that it does. There's one little kink in the tail. Because this is a dot product, can't you sometimes get negative numbers as well as positive numbers? So if the answer is -10, will you just remember to make it +10 because it's a physical volume? We can get around that by sticking absolute values around it. I don't like sticking absolute values around it because people then think it's the magnitude of a vector. And it's really not a vector, isn't that a scalar, right? It's just a number. But I mean, if you feel you need to, you can certainly do it. Now, that's one version. Very rarely, but sometimes you get this triple product and the answer ends up being the number 0. And that is also something that you can interpret geometrically. What do you think is happening when 3 vectors have a triple product of 0?
That they're only on a 2-dimensional plane, so
Yes.
it's not thick.
And we call that coplanar. Now, what coplanar looks like, can you imagine a flat piece of paper? It'd be an angle, right? It's not necessarily horizontal. Can you imagine the A, B, and C are all on the same plane? If this thing was going to have a volume of 0, wouldn't the vector A have to flatten down and be on the floor? Would that make sense? And if A had flattened down and was on the floor, wouldn't it be in the same piece of paper as B and C? Coplanar. So there is a test for coplanar. So if I give you 3 vectors and I ask you, are these 3 vectors coplanar? You will interpret that as, I am going to find the triple product. And if the answer is 0, I'm going to say, yes, it is. And if the answer is any other number, I'm going to say, no, they are not coplanar. Are we cool with that? So there's another reason to find triple products using cross products. So the one I'm going to pick is in front of me. It's question 20. And the vector A is 1, 2, 2, at least in my question. The vector B is -1, 1, 3. And the vector C is 3, 1, 2. Now, if this ends up being -10, will you remember what I said? That just means the volume is +10. Right? I'm not saying it is. Actually, it's not now that I've looked at the answer. But here it goes. A dot B cross C is equal to, well, a whole load of work. Won't I have to find B cross C first? So I'm going to go I, J, and K. And -1, 1, 3, and 3, 1, 2. And it's going to be so many I's. Take away so many J's. Plus so many K's. I'll cover that guy up. 2 take away 3 is -1. -2 take away 9 is -11. And -1 take away 3 is -4. So we get -1, 11, -4. And the dot product then is 1, 2, 2, dot product with this guy, -1, 11, -4. And that's going to get me 1 times -1 plus 2 times 11 plus 2 times -4. And that's 22 to 21, 8, 9, 9 away from 22. And the answer is 13. And I got it right, it's 13. So the volume of the parallelepiped would be 13 cubic, meters, whatever the units happen to be. And question 21 is a parallelepiped question. 22 is a parallelepiped question. Let's do a coplanar question, which is question 23 now. So I've got a vector u, which is 1, 3, -2. I have a vector v, 2, -1, 0, and a vector w, which is 4, 5, -4. We're being asked, are they coplanar? So if the triple product is 0, the answer will be they are coplanar. And if it's any other number in the universe, it's not coplanar. So I am going to do u dot v cross w. Oh. Before I do this question, there's a property that I haven't told you about. Do you know that when you do cross products, v cross w and w cross v, right, give you negatives of each other, right? So you don't get the same answer. A cross B is not exactly the same as B cross A. So the commutative property is dangerous, right? You can change the order of these guys. And this guy will be identical, provided you do that. Does that make sense? Provided you take the absolute value of them. So triple products don't care which two you do the cross product with and which one you do the dot product with, right? As long as you make sure that the answer is the absolute value. Now, if you are interested in coplanar, you don't even care about the answer being plus or minus, do you? Because if it's a number, it ain't coplanar. So who cares if it's 3 or -3? So there's a lot more flexibility. Now, the reason I'm pushing that is not for this question, but can you imagine there might be a question where if you did it in one order, the numbers come out a lot easier than if you did it in a different order. I'll give you a pretend version of that. Suppose U was 17, 15, 13, and V was 1, 0, 1, and W was 0, 0, 2, just for argument's sake. Wouldn't it be a good idea to do a cross product of V and W rather than U and V or any of the others? So you might want to just have a look and see if there's anybody out there. Cross products play well with zeros. Don't you tend to get easier calculations? So in this particular case, I don't think there's any reason to switch the order, so I'm going to use that one. And I have just realized something. I'm looking at the time here. I think we have enough time to do this one. And then I have to kind of rush to the next one. I, J, and K. So 2, -1 and 0, 4, 5, -4. this fella. Take away this fella. What's this fella? Are cross products becoming second nature now? You know, you do it without thinking. I hope that's what I would want. Okay, 4 take away 0 is just 4. -8 take away 0 is -8. Would you agree that 0 makes your life a little bit easier? And
Isn't the 4 negative?
Ooh, is the 4 negative? This one?
For the I.
Yes, but -4 times -1 is +4. If that's what you're telling me. Is there another 4 I screwed up?
No, you're right. My negative was weird.
Okay, that's fine. -8 take away none, done that one. Last one, 10 take away -4 gives me 14. So I'm looking at 4, +8, +14. And so what am I going to do now is U dot this guy. So it's going to be 1, 3, -2 dot product with the answer we just found. And that's 1 times 4 plus 3 times 8. Take away 2 times 14. And that's 4, add 24, take away 20. It is so nice when things come out. Coplanar. Oh. Now, if I gave you 3 vectors and I said, prove to me, prove that they're coplanar, would you agree if we didn't have this nice little result, it would be a much more difficult problem? I'm not even sure where to start, right? Because technically, aren't all 2 vectors coplanar? Right? If you've only got 2 vectors, aren't they always going to be coplanar? There's always going to be a plane going through them, right? No matter where they are, unless they're identical, I guess. But what would you do about third one? That would be a puzzle to me. They're just triple products. 25 is triple products with coordinates, so that's nothing really. 26. Yeah. In question 26, they just ask you, I guess I should start this, but I want to do one more question after this while I have time. Yes, I will. Okay. In question 26, they ask you to prove that all 4 points, A, B, C, and D, are on the same plane. So imagine this paper is slanted, right? What they're saying is that if you plotted A, B, C, and D, all 4 points would be on this piece of paper. Does that kind of make sense what they're asking you, right? That are they all on the same plane? Plane is just the name we give for a 2-dimensional, like flat piece of paper in 3D space. So if you imagine all 4 points could be on it. And so how do we do that? Well, we use the coplanar trick. Can I find the vector AB, AC, and AD? If I prove to you that those 3 vectors are coplanar, haven't I also proved to you that A, B, C, and D are on the same plane? Does that make sense? How I'm going to approach that? So the question was asking, are these 4 points on the same plane? And I've converted it into proving that those 3 vectors are coplanar. So my vectors are going to be AB, AC, and AD. Okay, 6 take away 3 is 3. -2 take away 2 is -4. 6 take away 1 is 5. Done. 8 take away 3 is 5. 1 take away 2 is -1. 0 take away that guy is also -1. 5 take away 3 is 2. 5 take away 2 is 3. -5 take away 1 is -6. And we are now going to do the triple product. Since none of these guys have zeros, I might as well just do it in the order that they're written. But if one of these had a 0 in it, or even better, 2 zeros in it, wouldn't I put that guy in the cross product side? Just to make my calculations easier. So let's get AC cross AD. So it's going to be I, J, and K. And this one goes first, and this one goes underneath. Then we're going to do the so many I's, take away so many J's, plus so many K's. Cover this guy up. That's +6, take away -3, so it gets me 9. That is -30, take away -2 is add 2, so it's -28. And this guy is 15, take away -2, so that's 17. And this is 9, this is +28, and this is 17. Now, if this doesn't work, it's just because I can't count, right? The process is correct. So AB is 3, -4, 5. Dot product with this guy, 9, 28, and 17. And I didn't give myself enough room, so I'm going to do the working up here. 3 times 9 plus -4 times 28 plus 5 times 17. Okay. 27, take away 112, add 85. Am I good or am I good? It's 0. And 0 means those 3 vectors are coplanar. And because those 3 vectors are coplanar, haven't I now proved that all 4 points are in the same plane? As an added bonus, I am going to attempt to do a question that's not in the homework. I am going to do torque. So we have, I know it's scary. We have a spanner. What way will I do the spanner? Right, I'm pushing the spanner down in that 3-dimensional direction. 1, 2, -3. Okay, and this thing here is going to be the direction that the spanner is in, right? The orientation of the spanner, and this is in the orientation 2, 1, 3. Now 2, 1, 8 there. So can you imagine that you've got a spanner that's like this? Wrench, I'll call it a wrench for Americans. Spanner is what we call it in Britain, right? You got a wrench, this wrench, and I'm pulling on it in this direction. And I am causing something to happen down here, right? And that thing is torque. And torque is that guy. And it even has a Greek letter called tau. It's a bit like a D. And tau, the torque, is the cross product of those two vectors. See, I can do engineering stuff. Actually, aren't I just finding the magnitude of a cross product? But it started life off as an engineering story. So here goes. Ooh, I have to be careful. I believe it's A cross B. So it's going to be I, J, and K. And it's going to be 2, 1, 8, 1, 2, -3. So many I's, take away so many J's, plus so many K's. Plus my wee, where's my wee guy gone? Cover that guy up. -3 take away 16, -19. -6 take away 8, right, -6 take away 8, -14. And 4 take away 1 gets me 3. And so I have -19, +14, 3. And the magnitude of that vector, which is what the torque is the square root of -19 squared plus 14 squared plus 9. And that's going to be the square root. I won't do that. I'll do 19 squared. Add 14 squared. Add 9. And it's the square root of 566. And since we're engineers, the answer is 23.8. I have no idea what the units of torque are, but they're probably a force unit, so I'll say it's newtons.
It's a force and length. Force unit times a length unit. So if you're working in Newton, in metric, it'd be Newton meters. If you're working in imperial, it'd be foot pounds.
So it'd be 23.8 Newton meters would be the torque that is going on down here. I guess that's the amount of force that you're trying to unscrew the nut with. So see when you get those things that you put wheels on with and they talk about the torque is 14 pounds or something, do they mean this number is 14?
I don't know enough to accurately say that, but
Maybe.
A foot pound is a force of 1 pound applied to 1 foot away from your moment of 1 foot. That is
Right. So what I was saying is if you had nuts on a vehicle and the torque on them had to be 50.
well, like lug nuts when you're
Yeah.
yeah, they're really saying in like Newton meters or foot pounds or whatever it is.
Right. So you could figure out what torque you were doing by knowing how long your lever is, which is basically this vector, and what direction you were pushing down on this side.
Mhm.
And that combination would generate the moment, which would become your torque. See the cool things we learn in this class? Molly, you're going to go out and find a truck now and do some torque on it just to check this out, right?
Sure.
Okay. I find it hard to believe that you might do that, but go for it if you feel like it. I think we've covered everything. I'm pretty sure we have. The last two are videos. I like finishing with videos so you can see someone else's way of doing things, or at least maybe a different way. And that is it. You are finished. Last name and bye-bye. I'll hang about if there's any questions. Tessa, bye-bye. Did we learn some cool stuff today? Good. Rosie,
The
did we?
coolest.
Say again, Rose, Tessa?
The coolest.
Ah, perfect answer.
Have a great weekend.
You too. Rosie, did we learn some cool stuff to do with torque today?
Yes,
And
very cool.
What about
Real world
parallelepiped?
applications.
Come on, parallelepiped. Is that not an interesting
That's
object?
the word of the year.
It should be.
Parallelepiped.
If you ever have kids, name one of them parallelepiped.
I will.
Okay.
Sounds
So-
like a Lord of the Rings character.
It does, doesn't it? It just sounds to me like it should have been a hobbit or something. I'm assuming that you know Lord of the Rings, right? Okay. All right, who's got the question? Who wants to go first? Unless
I'm
it's some
Just
personal.
here to,
basis.
I'm just here to see if somebody else has a question so that I can
Okay.
get the steal the
Right.
information.
Do you have a question, Rosie, or is it something you just want to talk to me
Yes, I
about?
have a question on number 13 from the 12.3 homework. Find the
Okay.
three angle measures to the nearest degree with the given vertices of A is 1, 0, -1, B is 4, -5, 0, and C is 1, 4, 4.
Okay. Let's find the size of the three angles. I think you said to nearest whole number.
Yeah, nearest degree.
Nearest degree, nearest whole number of degree. Okay, so I'll visualize it. I'll pretend that's where A is in 3D. There's B. Down here is C. And so the first angle I'm going to get is this angle here. I'll just call it theta. And the first thing you have to make sure is that if you want to find the angle between, say, AB and AC, as I do here, this angle theta, that you vectors I'm going to have to use are AB and AC. So AB is 3, -5, and 1. And if I do AC, it's 1 take away 1, which is 0. 4 take away that is 4. 4 take away that is 5. So far, so good. And now you can find the angle between any two vectors using the dot product. And the formula for it is that the cosine of that angle, which I'm calling theta, is the dot product of AB and AC divided by the magnitude of AB times the magnitude of the vector AC. Might as well do the magnitudes of these two vectors. This is 9 plus 1 plus 25, so that's the square root of 35. And this one is nothing, 16 and 25, so that's the square root of 41. So we have square root of 35 times the square root of 41. And if I do the dot product, it's 3 times nothing plus -5 times 4 plus 1 times 5. So I get -20 add 15. I get -15 over the square root of 35 times the square root of 41. We still good on this? Right. So what I'm now going to do is I'm going to find the inverse cosine of that guy. Inverse cosine of -15 on the top divided by, put a bracket around it, the square root of 35, close the brackets, times the square root of 41, close the circle brackets, hit enter, and I get the answer to the nearest whole number, 113 degrees. Did you try that pretty much the way I just did this one? I'm just trying to figure out where you went wrong or what you weren't sure to do.
It's when it comes to it's like the second and
Okay,
third
look.
lines that you've written where you're getting like all the numbers to plug into the cosine 0 formula. I always get that wrong.
Is it you're getting these two guys wrong?
Yeah,
Right. So if I was doing AB, I just go, I call it second, take away the first. Second, take away the first. 4, take away 1, 3. -5, take away 0, -5. 0, take away -1, 1. I mean, maybe you should write it down as a calculation first and then do the calculation second. Maybe, you know, try to do both in your head, maybe not working right now.
yeah, I write each step down and then,
It's still not coming out?
no,
Oh,
problem was it?
you didn't get 113 degrees, I'm assuming then?
No, I didn't even get that far.
Okay. Are we good then?
Yeah.
Is this making sense? Okay. So let's move on to finding a second angle. Do you want to find B or C? It doesn't matter, the method works. What do you want next?
Oh, how about angle B?
Okay, so I'm going to just call that guy theta again, because might as well call it theta, right? Have you noticed that this guy is now known, right? So if you're going to do angle B, the world does change. The two vectors that I need to use are vector BA and BC. If you want to find the angle between two lines, do you notice that you start at the middle and you leave in both directions? It's an outwards movement. Now you may say, well, that won't make a big difference. It can, because you might get the answer 50 degrees when really it was 130, right? Because the way that you chose to call them A, B, and not BA does make a difference. Now, if you want to do BA, which is the one I'm going to look at, BA, notice A is second, so I go second, take away first. So it's going to be 1, take away 4. 0, take away -5. -1, take away 0. Now, if I want to do BC, which is here, BC, this guy is the second. So second, take away the first, -3. 4, take away -5, 9. 4, take away, I'm assuming that's a 0. 4, take away 0 is 4. So here are going to be the two vectors that are going to help me get this missing angle B. The magnitude of this vector is 9 plus 1 plus 25, so it's the square root of 45. The magnitude of this vector is 981, so that's 90, and 16, so it's 106. So I can now go and do the cosine. It's BA dot BC over the magnitude of BA times the magnitude BC. The two magnitudes are square root of 45 and square root of 106. And the dot product, well, -3 times -3 plus 5 times 9 plus -1 times 4. And that's going to get me a 9, add a 45, take away a 4 over these two guys. And what does that get me? That gets me, oh, that gets me 50. It's not as bad as I thought. So to get the angle, I do the inverse cosine of that guy. So I go at my calculator and I go inverse cosine of the square root of 45 times the square root of square root of 106. And the answer, oops, I hit something wrong there. Do it again. Inverse cosine of 50 divided by square root of 45 times square root of 106. There we go. And the answer I get is about 44 degrees when you round it up. And now we have this one. And then I save some time. How will I get the third one without doing too much work?
I know with 2D geometry, you just subtract the two angle measures from 180.
And
But
this is correct. This is still true even in 3D, because although this is 3D geometry, this triangle is a two-dimensional triangle in 3 dimensions, so it's still 2D. And so what you said is right. So what's that? 157, so it's 23. And that is pretty much how you do that question.
Okay. I was having a lot of trouble on 17 with
Okay.
setting up
Well, okay. What was
PQ and
right, so 17?
it's a triangle with vertices of point P, 1, -3, -2, point Q of 2, 0, -4, and R, which is 6, -2, -5. You're determining if it's orthogonal.
Okay, so what we're going to be doing here is finding out if this triangle is a right angle triangle or not, right? That's just orthogonal, just means in the world we live in right now, the 3D world, it's 3. So in a lot of ways, it's very like the question we just did. Can't I just find the sizes of those angles? And if one of those angles is 90 degrees, does it not mean that it's orthogonal? Right? So we're going to try and get lucky. And I know we won't be, but we'll try. Which one of those 3 might be the right angle? And I know the way I've drawn the picture has nothing to do with reality, so it's really a lucky guess. P, Q, or R, which one might be the right angle? Just a guess.
Q.
Okay, now let's find angle Q then. So to get angle Q, won't we have to find QP and QR? Agreed? And QP is going to be, this is going to be the first guy, and this is going to be second. So it's going to go, right? Second, take away the first. Second, take away the first. Second, take away the first. So it was 1 take away 2, -3 take away 0, and -2 take away -4. Now QR is going to be second take away the first, so 6 take away 2, -2 take away 0, and -5 take away -4 gives you 1. And this guy is now going to be the square root of 9, 10, 14. And this guy is going to be the square root of 16, 21. So far, so good?
Yeah.
So the cosine of theta is going to be the dot product of these two divided by the magnitude of these two. And the dot product is going to be -1 times 4 plus -3 times -2 plus 2 times 1 all over the square root of 14 times the square root of 21. And there's a number of different ways to solve this question. We're just continuing with this one because it's the way I started. But what do I get in the top? I get -4, add 6, add 2. Oh, I was disappointed there. I thought we had it. And that ends up getting us 4. So here we go, inverse cosine then. So inverse cosine of 4 divided by, put a bracket around it, the square root of 14 times the square root of 21. And the answer we get is about 70, I'll go 1 decimal place, 76.5 degrees. Okay, we know it's not that one, but it could still be right angled, agreed? So to save time, because I want to show you other methods, couldn't I then go and try and find the size of angle P? And if it was 90, wouldn't the answer be you've got a right angle triangle? And let's say I found the angle P and it was 13.5 degrees. Just pretend it was 13.5 degrees. Couldn't I then find what's left by adding the 2 I know? And guess what? If it was 13.5 degrees, angle R would have been the 90-degree one that we're looking for. Now, if it wasn't 13.5, if it was some other number, wouldn't this be some other number? And you'd be looking at 3 angles, none of which are 90, and that would mean, forget it, it isn't right angled. So that would be approach number 1. Find the size of all 3 angles. The only one I really truly did correctly was 76.5, and I just pretended what the other 2 were, right, for speed reasons. Now, same information, I'm going to tackle it a different way.